Now continuing, let's go to page 316 where we're going to prove the Kepler's law of planets, which states that a planet going around the sun has an elliptical orbit. Now to prove that, first let's look at what is that? I want to mention the quotient rule for vectors. The quotient rule is not explicitly mentioned, but it's the same as the product rule. See, any quotient rule is just the product rule of a function where you're multiplying the f of t is actually a fraction. You just substitute it as some fraction, and then the product rule applies. Now in this thing I wrote down, the f is just a scalar function, whereas u is some vector function. But as you remember, the product rule for this kind of thing works the same as the product rule for normal functions. So, so if you plug it in, then you can quickly do following the product rule and get that the same quotient rule applies. Okay, you will come up with this thing very quickly. For the same reasons that the regular quotient rule applies, the quotient rule for a product and the scalar function applies the same way. So that's I just want to remind you of that because the book didn't explicitly say that. And next, I want to talk about something called the triple cross product, which states that when you have u cross right here, u cross v, v cross w, it happens to be equal to this thing right here. Okay, now let me show you why that is. Now this thing is called, the book calls it what? The triple cross product. The internet calls it the vector cross product. The vector triple product. And I found the proof of it because the book has either neglected or something and didn't really show how this comes out. Now to prove something like this, what you do is you go back to the definition. That is, you figure out what is the triple product by hand. Okay, you have 3 random vectors. Let me show you what that is. You have 3 random vectors. Now in this proof, the cross product is denoted by that upward arrow instead of a cross, but the idea is the same. So what you do is you write it out what it is and write the whole thing out, which is a big long pile of stuff, right? And then what you're going to do is write out the other side and then write out the other side, that is, write out what this thing represents. Okay, here's the second half of that proof. You write out the other side and then you say, oh wow, check this, the 2 sides are the same. So that is how you prove the triple cross product, also called the vector triple product. We are going to need that in proving the Kepler's law of planets. So I just want to mention it because the book didn't exactly explain how that works, but the way it works is very simple. You just work on both sides until it comes out. And then, maybe not quite simple because you're talking about a lot of writings, right? But it's straightforward. You know, you just do it and it'll come out like driving 1,000 miles. And then this is the scalar triple product, which we already had, but I want to write it here to remind you. And again, V is defined as dr by dt, right? We have already known that, but I just want to remind you of that. Now, having said that, the next thing I want to mention is the equation for conic sections. Now in conic sections, we have in polar coordinates, we were taught that the equation of a conic section, which includes an ellipse, is something like this: r equal to ep over 1 plus or minus e cosine theta. Now the e stands for eccentricity, okay, and not the logarithm e. So then and we don't need to know too much about that right now. Just this is just a quick refreshing idea, recalling that formula vaguely, somewhat. So having said that, we can start proving the Kepler's law of motion, which is that the planet, the orbit of a planet around the sun is an ellipse. So first, we are going to start with a formula from Newton, which is F equal to ma, all right? And that end up being this thing. Now we are therefore, so this thing. Now we don't know what these numbers are, but they are just numbers. And the book doesn't even bother to explain what it is. Okay, but I will quickly mention that this is the mass of the sun, and that's the mass of the planet, and that's some gravitational constant, I believe. Nothing matters. Like I said, this is the book doesn't explain it, so I won't either. I mean, I don't need to either explain it to any accuracy. Because our goal here isn't to study physics. We are studying math, okay? So how are we gonna, regardless of what that is, we're gonna calculate that orbit. So that we are going to first figure out A. What was A again? A is V prime of t as to by definition, right? So first step is V prime of t times m is going to be equal to this whole thing here, our first step. And then that means we can divide out the small m and get to the next step, which is, we'll rewrite that as dv by dt equals to minus gm. Again, gm are numbers that we don't care what it is. Divided by, we'll round these together, so we have 3 of them. R3, R is the position vector, and times r. All right. So far so good. Next, we are going to see that because dv by dt and r are equal, as you can see, dv by dt is some constant times r. That means they are in the same direction. They're parallel. And therefore, the next step is we know that dv by dt, which is a vector, everything here in here are vectors, even though I don't put a vector signal on them because that's too much work. dv by dt cross r has to be equal to 0. That's the cross product. The reason is because parallel lines collapses and it doesn't draw a parallelogram. See, and that's the cross product is parallel vectors have 0 cross products. It's that simple. And next, let's take the derivative of something, r cross v. So here's the first step. We'll stop right here. Now we are going to take the derivative of r cross v. And remember, v is r prime. That is our dr by dt, right? Okay. Now, why are we doing that? No reason. We're just going to do that. So let's take the derivative of dr by dt, which we haven't done that much of. Okay, so which is why this proof is excellent for us to get used to manipulate vectors and using some or many of the properties of vectors that we've learned. Get used to it. Anyway, so we are calculating the r cross v, and we're going to take the derivative of that. Now, to do that, we are going to apply the derivative rules, which states that we can take the derivative in order, right? Just like the regular product, we'll do the r cross v, dr dt cross v, and then r cross dv by dt. And as long as you don't flip the orders around and do things in that order, everything looks good. And then what is dr by dt again? The first term, dr by dt, remember, that is just v. So we have dr by dt is equal to v, right? And the second time, r cross dv by dt. The first term is dr by dt, all right? V cross v. And then the second term is r cross dv by dt, which is 0, as we just mentioned, plus 0. And so that is just v cross v. And what is v cross v? Any vector crossing itself is 0. So then, so this thing equals 0. And this is a 0 vector. So is that. Anyway, so that's why your book has it in boldface. But the point of doing this is we're showing that r cross v is a constant vector. I mean, yeah, because the derivative is 0, right? So the vector must be r cross v is a constant. If it's a constant, then we will call it c. So we will call r cross v equal to c, where c is some constant. Constant, please. So c. So now we have to establish that r cross v is a constant. C constant? Good, no? Now, and also, since R cross V are both perpendicular to C, then because C is a third vector, you cross product and come up with a third one, and the result of a cross product proves that, and C being constant means R cross V is always perpendicular to a constant. And that for no matter how the value of t changes, because R is a vector function of t, and so is v. But no matter how t changes, it's always perpendicular to this constant. Each of them, both of them are perpendicular to this constant, and that proves that they lie in a plane that is perpendicular to c. And therefore, now we have just proved that the motion of R was what? R was the path of that planet, okay, the orbit that we're calculating, which means the orbit of the planet, even though it's in space, it's not jerking all over the place. It stays in a proper plane. We don't, or it might not be round, but it's in some plane. It's not wobbling all over the place. So far we have figured out that the path is in a plane. The next step is that we need to prove that that path is an ellipse. So let's move on. So far so good. Now next we're going to calculate dv by dt cross c. So we'll calculate this thing, dv by dt, and we're going to cross it with c. C is this thing we just cranked out just now. And why? Because we feel like it. Okay, so let's calculate that. And what do we have? And going back to what was dv by dt is this thing right here. Okay, so we write that down. And then cross c. What is c? C is this thing right here. So we write that down. And then we are going to, so we have two cross products, right? We have R cross V, as your book has written down in the middle here. So we have, and how are we going to do that? We are now going to apply the, what do they call it? The triple cross product that I wrote down right here. Okay, plug all that in. So what you have is we will have write down the constant out front. Okay, all this stuff, this pile of junk here, this is all constant. I mean, this pile of constants here. Our Q power. Okay, write down the constant. Now we have to do R cross V. Following this rule here, then we get R cross V. R dot V. All right, it becomes R dot V times R, yes, minus R dot R times V. Okay, following directly the triple cross formula, and that should be right. So then next we are going to, the book says that, oh, you just click to that chapter and you'll find it. No, you won't, because I looked. And anyways, but we'll move on. Nowadays we got the internet, right? If the book makes a small mistake, we can dig it out ourselves and fix the problem. Not a big deal. See, studying math is so much more fun nowadays than it was in my day. Anyway, so let's move on. Now next we are going to figure out what R dot V is. Okay, to calculate this, we differentiate. We're going to do some differentiation. So figure out. What we're going to do is take the derivative of R dot R. So we're going to calculate d by dt R dot R and see what happens. And by now you might be wondering, what are we doing again? We are calculating the orbit of a planet around the sun. All right. So having said that, we will calculate what dt R dot R is. What is it? R dot R, as we'll apply the product rule. Okay, the product rule for dot product is very simple. You just start it like a regular product rule, plus you can flip it around, because dot product doesn't mind being flipped around, so everything comes out nicely. So if you do that, then right here, okay, then it becomes so you get two identical objects, right? you end up with 2r dr by dt, and which is 2r dot v, because dr by dt is v. So we get this result. What happened to my marker? Found the marker. So that equals to 2r dr by dt, and which is, of course, 2r dot v. This is a dot product, and well, from over here, okay? And then, so far so good. And also, we notice that r dot r is, what is r dot r again? R dot r is just magnitude squared, okay? That's the property of a dot product. So then d of r is the derivative of that thing, okay? So let's write that down. So d by dt of r squared, magnitude of r squared, which is r dot r, okay, and is equal to, now we're gonna apply the chain rule. Now we've never actually done that directly before, but the concept is simple. The concept, however, is a scalar product. This is not a vector because it's the magnitude. It's a function of t. So as a function of t, we'll apply the chain rule, yes, which is 2 times this object, right? 2 times what's inside, and then times the derivative of what's inside, d by dt of this thing. All right, so I'm just applying a basic chain rule here. Yeah, so we got that. So now this thing right here is the same as this thing down here. And then let's see what do we do next. I lost my spot. Where'd it go? Or we'll put those 2 things together. That means r dot, what was this? This is r dot v. Okay, so then r dot v is equal to that thing right here. We'll get rid of the 2 because there's a 2 on both sides. The magnitude by dt. All right. So we got to the end of the page. And so far so good. And let's go to the next page. What? Okay, now we're gonna do some substituting. What are we substituting? Substituting dv by this thing right here. We have this thing, all right, and then we need to substitute r dot v, which is right here, okay, and then r dot r, that's just the magnitude. So we'll write that down. Should I write it down? Sure. All right, so I wrote it down. Now, I'm following this, plugging stuff back down into this formula right here. Okay, this is a bunch of numbers, and then we have r dot v, which we figured out right here. So we plug this whole thing into r dot v. So I wrote it down right here. See, this is r dot v, which is to be dotted with, which is to be multiplied by r. It's not dotted because r dot v is just a number, a scalar function. And then minus r dot r. R dot r is r squared. Okay, the definition of dot product. The magnitude of the dot product. And so r dot r is r squared and times v. So that, which is give us that particular equation. And then if we clean this thing out a little bit, then we have, well, how are we going to clean it out? Well, let's look at it. You have, okay, negative. We'll just look at this here and do some simple algebra. Straightforward algebra. Now, it's not that simple, I guess. However, see, you have dividing by r cubed, a magnitude r cubed at the bottom. There's an r here, one of them here, so you're left with 2. Okay, and the other side is you have 2 on top, right? So once you put it in, then you have only 1 left. on the bottom. And then you flip it around. Write this thing, write this term in front. Get rid of the minus sign over here. So let's get rid of minus sign. So you just flip around, write this thing in front, and write that chunk. My camera is having trouble because of my hand, I think. Anyway, so write the other chunk at the back. And anyway, oh, there it is. Okay, yeah, write the other chunk at the back, and we get to this point right here, which I will also write it down. All right, now that I've written it down, now take a look at this thing. We have a bunch of stuff, and we need to figure out what this thing is, right? Actually, no, we're gonna now do something else, I guess. We're gonna take the derivative of r over magnitude of r. Why? The reason will be shown in a second. So let's calculate the derivative of, actually, I'm not even gonna write it down. The point is, we're gonna take the derivative, I'll write it down to show you. Derivative d by dt, okay, of r over the magnitude of r. Why? Because, well, anyway, let's take the derivative and figure out why later. Now, to take the derivative of this thing, this is a fraction, okay? So we'll apply the quotient rule that I mentioned a little earlier, which is the same as any other quotient rule. And then we, so that's the quotient rule on top. As you can notice, it's very familiar looking. That's because it's the exact same thing. And then we clean it up a little. And we have dr by dt, and break it into two fractions. One side is dr by dt over magnitude of r. The other side is, well, the rest of that stuff, okay? And then, of course, dr by dt is v over r, and so on, and equal to the rest of that stuff. Now, look at that very carefully. You notice that that is exactly in here, what's in here, term by term identical, see? So as a result, then we can say that, so we plug this the derivative of this thing right into this formula right here, and we write it down here to become, all right, so I have substituted this whole thing with that because we just demonstrated it by applying the quotient rule. This thing is exactly the same as that thing, and v being dr by dt, as I mentioned earlier, right? So this all works out. So we got down to here, and the next thing we are going to do is integrate. We're going to stick the integral sign on both sides to get rid of the derivative. The reason we can do that, even though we haven't really formally done anything like it, it's just that because you're crossing a constant, as you imagine, when you cross a constant, you do plus and stuff of with a bunch of constants. So the function, nothing really changes. And as a result, we can, this is going to be equal to v cross c, okay? You just, in other words, you just integrate this thing and then do the crossing. Makes no difference if you do it, if you integrate the whole thing or integrate this first and then cross. So that will establish. So when we integrate both sides, then it equals to gm, and then just r over magnitude of r. Where's my absolute value? Okay, and then you have to remember your constant of that constant of what is called the constant of integration, right? Indefinite integral. You got to not forget that constant. So we have a constant, and so far so good. Where d is the constant vector, and then now we're gonna solve for r. All right, so to solve for r, we are going to calculate the next step. We're going to calculate r dot v cross c. So we're going to take r and dot it. Where is it? Okay, so we'll do r dot v cross c, which equals to whatever. Now, when you do r dot v cross c, then r dot all the stuff, okay? And let's look at the algebra of this matter. Now, if you take r dot v cross c, then r dot that pile of stuff, we'll dot each one at a time. The first one, r dot r, it becomes over there, r squared, okay? And the second one, r dot d, that's just r dot d. And then when the squared divided by the one on the bottom, then you just have one left. So we have that much cleaner looking thing, GM magnitude of r plus rd. All right, so I have it written down right here, and the much cleaner condition. Next, we are going to consider the fact that this condition, okay, we're going to move the cross product over like this. So we have our cross V equal, then cross C, cross, right? Yes, we'll stick the R cross V in front. And then now we have this thing also equal to that. And next we are going to say that R cross V, what was that again? R cross V is defined as C. That's where we got C out of. So this part is equal to C, okay? And then we have, let's see, sorry, there's a dot product, right? This is, yeah, dot, not cross. So this is a dot. And that means this is C dot C. And what's C dot C? Well, that is the magnitude of C. So we get the whole thing is equal to the magnitude of C squared. So the magnitude of C squared is equal to all the stuff. Okay, so far so great. And then we're going to figure out what R dot D is. And so eventually what we get is this. Now R dot D, by definition of the dot product, or by some formula of the dot product, R dot D is RD cosine theta, right? Right. Where theta is some angle between R and D, all right? So then we conclude that the magnitude of C squared, okay, is equal to this stuff right here. Over here, we'll rewrite it as GM and the magnitude of R plus R dot D is RD cosine theta. RD in magnitudes, lots of magnitudes, cosine theta. All right, I believe we have come to the end. Now at this point, then we plug the R out of here. See, we have, this is all numbers now. There's no more vectors left, right? It's magnitudes of stuff. So we plug R out of there, and then we get this equation right here. As your book has shown, there's the bottom equation. And see, our magnitude of R is C squared, etc., and equals to that thing. And what is that? That is the polar coordinate of some ellipse. It's not necessarily ellipse, it's some conic section, but we're just going to call it an ellipse here because we are no longer concerned with it. Okay, because the whole this whole process is to show you how to manipulate vector, well, working with vectors. It's a great practice to do vectors. We have used the various products and the different definitions and all that stuff. See, we took the derivative, we even integrated, you see. I mean, it's just so nice. We have used, basically, we've used a lot of the stuff I learned and practiced how to use it. So that's why this is a very cool proof of the Kepler's law of motion. In reality, I don't think it's near as hard, you know, I mean, to prove in physics, you're not going to be doing this, I don't think. Well, at least I don't remember doing this. I mean, it's just an ellipse. What's the big deal? You know, you just calculate the ellipse and it will come out very quickly. There's no need to go through all this. But the reason I want to go through it is because this is all very cool proof, right? And and very neat. And you pull all kinds of tricks to get to the result. And it's a good way to show off how much we know how to use the vector calculus. So that's that. That marks the end of this proof. So let's go to the next page where we have example 3.17. Let's skip that because there's neither vector nor calculus in this thing. And the next one, example, same thing. Let's skip it, okay? Because we just want to go through the proof to enjoy vector calculus. We don't really care about the physics of it. So it's an ellipse, you know. And what's the big deal? We know we've worked on ellipses like, what, 3 times in 3 different courses or something? That's enough for anybody. So let's get to the homework. Now for homework on page 324, please do problems 157, 161, 63, 65, 67. For 67, be sure you plot the graph for z up to 100. Otherwise, you can't see much. Okay, and I'll show you later what I mean. Now 183, 85, 89, 93, 95, and 201. Well, it's very interesting to do this proof, to actually use vector stuff. There's nothing like that. You don't have to do any of this. This is just to show you how cool it is. Some of the proofs can be, but the homework is mostly straightforward. It might be time consuming though. I don't know, but please go do your homework, and when you get back, we will talk about a couple of the problems. Now that you're done with this homework, I want to talk about a couple of the problems. 167. Working on the 167 is straightforward. You have to do the speed or something, follow some formula. I just want to plot this thing because the book did give you a plot, but I think that plot is misleading. So I typed it into the calculator. Okay, this is the 3D decimals, and then as you can see, I have t going from -7 to 20, and that gives us that graph. And that, you see, that graph looks really big. The spiral looks really fat. That's because the width of this thing is only 3. The x and y limits are only at 3, whereas the height here, I'm setting it at 40. See, so the whole thing is a very squashed look. It doesn't actually look like that. It looks really skinny, and you can't see very far because it goes up there fast. So I had to do this just to show how much of a spiral it really is. And then the next graph I want to show you is part 2. Yeah, and then when I increased z to 100, you know, right here, and then you can see the spiral is doing more spiraling. Okay, again, the width of this thing is only 3, and whereas the height is 100, so this is a squashed graph. And that's how you can. And if you change the numbers for this, the range of z, then you can, in the graphing, then you can see the graph much better to fit and to be fitting to the eyes, right? And in reality, of course, this is the super skinny thing that crawls around the z-axis. That's what, proportionally, that's the real picture. But it's still some kind of double spiral. It winds around up there and goes up fast. And so it's not a helix or anything because t is squared. I believe for helixes, the t has to be just t, some multiple of t instead of, it cannot be squared because squared makes it go up way too fast. And so that's all I want to say about that. Now the next problem I want to mention, not much worth mentioning, but I'll mention it, is problem 185. You're supposed to find out what is AT and what is AN. And you follow the formula on page 309, where AT is defined that way, V dot A over magnitude of V. So you figure out what, at some point, which in this case is t equal to 0. So V equal to 0, you figure that out. And then A equal to 0, you figure that out. And then you do V dot A and stuff. And you don't even have to divide by a magnitude of 0 because the whole thing is 0. So AT is 0. And then AN, we'll use the Pythagoras theorem. Okay, AN is just the magnitude of A, which is omega. That's not a W, by the way. That letter is called omega. It's a Greek letter. Okay, is pronounced omega. It's the same as the normal omega except small letters, and it looks like a W. And sometimes I might forget. But anyway, this is omega. So the answer is AN is A omega squared, and that's the right answer and marks the end of this section.